Welcome back to our geometry series. Today we are up to section 5.3 where we will be talking about the Pythagorean Theorem. So here's our good friend triangle ABC, and what I'm going to do is use lowercase letters to name the sides of the triangle. So here if you look at angle C, the side C is the hypotenuse. It's the angle that's opposite of the side. So capital letter A in the upper left has its counterpart lowercase a side on the bottom. It is opposite of the angle. So these lowercase letters also represent the measurements of the lengths of the side. So for example, lowercase a, the bottom of the triangle here, is equal to the length of segment CB. So let's remove the angles and only look at the sides, knowing that we are still working with a right triangle here. And that leads us to theorem 61. In a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. This is Pythagorean Theorem, named after Pythagoras, who discovered it. And here's a picture of Pythagoras looking swole. So this is a lot of words, so let's break this down. So let's start with the hypotenuse. The length is c, so we're going to find the square of it. So c times c squared. This is equal to the sum of the squares of the lengths of the legs. So a squared plus b squared will equal c squared. So let's take a look at an example. We have a triangle here. We have two sides, the legs, 3 and 4, and the hypotenuse is unknown. But by using the Pythagorean theorem, we know that x squared will equal 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16. We'll add those together, we'll get 25. So x squared is equal to 25. We'll take the square root and find that x is equal to 5. This is known as a Pythagorean triple. It consists of 3 positive integers, a, b, and c, such that c squared equals a squared plus b squared. And you'll see these from time to time. So some other examples are 5, 12, and 13, and 8, 15, and 17. Mathematically, x could also equal negative 5, because negative 5 times negative 5 is still 25. However, in the world of geometry, we're talking about lengths and distances, so negative numbers don't make any sense, so we're going to ignore this. So let's jump over the whiteboard and do some quick examples. Alright, I'm going to draw a rectangle here, like so. And we're going to say that this is 12 meters up here. And then I'm going to draw a diagonal, like so. And say that this is 13 meters. And we want to know how tall is the rectangle. Now the first clue is that we call this a rectangle. So we know that this is a right angle. And over here, we've got a right angle, and there's one over here, and I'm going to draw another one over here. So what we've created right here, if you look, is a right triangle. And we've also created one here. And because this is a rectangle, we know that this side and this side have to be the same length. So I'm going to put this as 12 meters as well. So now we have a right triangle, and we have a leg, and a hypotenuse. But we can use Pythagorean theorem to figure out what this leg side is. So let's just write this out. We're going to say that 13 squared, so the hypotenuse squared, is equal to x squared plus 12 squared. I've took this side, squared it, took this side, squared it. It's going to equal the hypotenuse squared. So we'll do some quick math here. 13 squared is 169. That's equal to still x squared plus 12 squared is 144. So using our good old algebra skills, we're going to subtract 144 from both sides, and that's going to equal x squared. So this is 25. So 25 equals x squared. I'm going to take the square root, of both sides, something like that, and we end up with 5 equals x, or x equals 5. Again, really, negative 5 is an answer, but we're going to ignore that. And here we end up with 5 meters. And it's one of those Pythagorean triples we talked about, 5, 12, 13. So that one came up like that. Okay, let's clean this off and do another example. Alright, and this one might look a little weird. We're going to start with a right triangle. I'm going to draw it like this, put the little right angle in here. This is x. This is what we're trying to find. The hypotenuse is the square root of 61. Okay, that's weird. And this length is x plus 1. So we're trying to find x. Oh, it's right there. See, I found it. No, we're actually going to find the value of x. So let's just write it out as the Pythagorean theorem. We're going to take the hypotenuse and square it. So I'm going to write it out. 61, the square root of 61, squared is equal to, we're going to take this side first, we're going to square it. X squared plus this side squared. So we'll use some parentheses to keep everything nice and happy and separated. So a squared, b squared equals c squared. Okay, so far so good. The next step, I'm going to take this. We have the square root of something squared. So we end up with, what you started with. So this just turns into a 61. If you take the square root of something and then square it, you just get the guts of the inside. So 61, that's easy. And I'm going to rewrite the x squared and then focus on this. So x plus 1 quantity squared. You could spell this out, you could FOIL it out. You end up with, and I'm going to leave it in parentheses again, x squared plus 2x plus 1. Remember algebra? Remember doing this stuff? So next, I'm going to combine the like terms here. I have an x squared and another x squared. These are like terms. So this turns into a 2x squared, plus the rest of the stuff, plus 2x plus 1 equals 61. So we're trying to find what x is. So we've got a quadratic equation here. We need to set this equal to 0 to find out what x could equal. So we need to subtract 61 from both sides. So let's just do that right now. I'm going to subtract 61, so this becomes 0. And we still have this term, we still have this term, and we have a negative 60 over here. Now we can simplify this expression. We could divide both sides by 2. So 0 divided by 2 is just 0. And if we divide this whole thing by 2, we get x squared plus x minus 30. Okay, so we're getting close here. If we look at this, this is something that we can factor. This factors into x plus 6 times x minus 5. Sorry for all the algebra, but this is a good example. So we have this is equal to 0. So remember, you have two things being multiplied that equal 0. So that means that this has to equal 0 or this has to equal 0. So we're getting two answers. So we have an x squared, so we end up with two answers here. So what would make this expression equal to 0? Well, it would be negative 6, because negative 6 plus 6 equals 0. So to make this expression 0, one of the possible answers is x equals, I'm still on the screen, negative 6. And here, x would have to equal 5. 5 minus 5 would make this 0. 0 times whatever this is equals 0. So x equals negative 6 and x equals 5. So if we were doing algebra, this would be the answer. We'd have two answers. However, we're talking about a physical thing over here. And this length can't be negative. So we can kind of just say, no, that's not going to happen. And x is 5. This length of this triangle is 5, this is 6, and this is the root of 61. Okay, let's clean this off and do another example. Okay, we're going to draw a triangle like so. Nice tall triangle. And then we're going to draw a line straight down, make a right triangle, and of course there's another one over here. And the length from here to here is 20. I'm going to make it look like this. So the base of this big triangle is 20. And what we're going to say is that this side and this side are the same length, and that length happens to be 26. And what we're trying to find is the height of this triangle that we have here. So the first clue is that we have this length of 26 is also this length. So I'm just going to write it down just so we see it, because the little marks tell us that this is the same as this. And we've learned in the past that when we have a altitude like this that comes straight down and is perpendicular to the base, we know that it's going to bisect this segment here. So what we can do is write in that this is 10 and this is 10. So really we've kind of created a, this is equal to this situation because of this. We have this isosceles triangle, the two sides being the same. This altitude that's perpendicular to the base is going to split the base in half. So we're trying to find the h. Now we have a nice right triangle here. We've got two of the three sides of the right triangle, so we can bust out some Pythagorean theorem here. So let's just write this out as 26 squared, the hypotenuse squared. It's going to be equal to the height squared, this h, plus 100 squared. So 26 squared is 676. This is equal to still h squared plus, well, 100. Oh, I didn't do that right. Well, it ends up being 100. Whoops. This is really 10 squared. 10 squared. Yep, is 100. I got a little anxious there. So we're going to subtract 100 from both sides. We end up with 576 equals h squared. I just took this 100, subtracted. So let's find the square root. So I'm going to take the square root of both sides. And h is equal to 24. So here's another Pythagorean triple. 10, 24, 26. I'm just going to write that down here. 10, 24, 26. That's a Pythagorean triple. And we're going to write this up here as 24.
That's a good use of the Pythagorean Theorem.
Thanks, Pythagoras. Now, get out of here. All right, let's clean this off and do another example. Alright, this one will take all my skill to draw correctly. We're going to draw a rectangular box. So this is a three-dimensional object. Something like, let's see here. Here's the top of the box. Okay? And like that. Oh, it's already going askew. And here's the side of the box. Like this. And here's the front of the box. Right? And we're going to use, little dashed lines to see the lines that we can't see that are behind the box. And here's a nice three-dimensional box. I'm also going to draw this diagonal on the side over here. Like that. And we need to put some markings on here. We're going to call this A, B, C is down here, D is over here. This is O. And that's it. We're going to focus on this face, really. We're not going to bother marking up the other sides of this rectangular box. So a rectangular box, I'm going to write that word down because it's important. Rectangular box. So what that means is that every face is a rectangle. What that means is that even though it doesn't look like it, something like this. This is a right angle between here and here. And we've got a right angle, here. All of these are right angles. So we end up making, here's a right triangle. So here's the big question. I'm going to connect this back corner of the box to this bottom front corner. So there's this funky diagonal going through the box from the front all the way to the back. And we want to find what is the measurement of AC. Well, we need some more numbers on here, don't we? So this back wall, we're going to say is 12. And this side wall is 4, and this top wall is 3. So because it's a rectangular box, we also have, opposite sides will be the same length. So like OC, this is 3, and BO is 4, and BD is also 3, right? So we have a lot of similar lengths. Actually, DC is 4. So we're trying to find this angle, right? How do we find from A to C? Well, it turns out that ABC is actually a right triangle. If you think about it, this is a right angle, right, between AB and BO. So this, BO, is in the same plane as BC. So it's kind of hard to see, but ABC is a right triangle, and the right angle is at angle B. So if we could find what BO is, we know what AB is. So we're going to have a right triangle, ABC. And this we're going to say this is a right triangle. All right, so we need to find out what BC is first. So we've got, let's look at the side of this rectangular box. We have BD and DC, and then, so we've got another right triangle, BDC, BDC. It's on the side of this box. And again, this is your right angle, the side of the box. So we have one leg, which is 3, one leg, which is 4, and we have the hypotenuse, BC. So BC, the measurement, is going to equal to BD, well, squared, plus DC squared. Let's just double check that. So BC, that's the hypotenuse of this right triangle on the side of the box. So BC is the hypotenuse. The hypotenuse squared is equal to one side, BD squared, plus DC, the other side, squared. So we know BD is 3 squared, and DC is 4 squared. So this is 9 and 16. It's that 3, 4, 5 triangle again. So we know that BC is equal to 5. So we can write that in here, 5. Okay, so we're getting there. Let's look back at triangle ABC. ABC. And I think we got some space down here. So AC is the hypotenuse of this right triangle, right? The right angle ABC. So AC, and we got room. I'm just going to put it way down here. AC squared is equal to AB squared plus BC squared. AC is the hypotenuse. And even though we're kind of cutting diagonally through this box, we still have a right triangle right here at angle B. So AC is what we're trying to find, okay, is equal to AB squared. AB squared. So 12 squared, it's getting cozy down here. Well, let's write it this way, equals 12 squared plus BC squared. BC is 5, equals 5 squared. This equals, I'm still on the screen, 144 plus 25. 145 is 169. So AC squared, we're just going to rewrite this, equals AC squared. So all we need to do is find the square root of 169, and we'll end up with AC, the length of this, super diagonal through the box. So the square root of 169 is 13, and we'll actually just kind of rewrite it like this. Take the square root of both sides, and we'll just put it over here in the corner that AC equals 13. Again, we ignore the negative 13 in this mathematical equation because we're talking about a real life length. So AC equals 13. And that's it for today. It's a pretty short section. We'll see you next time.